This video presentation is for high school general chemistry classes. It is about reaction rates and energy diagrams. Things covered in this presentation will be collision theory, reaction rates, potential energy diagrams, catalyst, and several other things that are included with potential energy diagrams, such as activation energy and activated complex and energy of reactants and products. These are the North Carolina Essential Standards unpacked for the topics covered in this presentation. If you would like to read over them, please pause the video and do so now. These are the student objectives, what the student should be able to do at the end of this lesson. They should be able to explain how reaction rates are affected using collision theory, and students should be able to interpret potential energy diagrams. So let's jump right in. Let's first start with collision theory. Collision theory states that the rate of reaction will be increased when the number of effective collisions increases. Now, there's two things that's really important to mention here with collision theory. Effective collisions, what does that mean? Well, it means two things. The particles have to have enough energy, and they actually also have to be oriented in the correct fashion. So an effective collision means that the particles have enough energy, but it also means that they have the correct orientation. So do they have enough energy? If we see this first example here, if the particles are moving too slow, they're just moving too slow, and they're not going to have the required energy needed to cause those bonds to break and for that reaction to occur, no reaction. Now, correct orientation. Let's look at the picture right here in the bottom left corner, because it's a little more clear. So we see, I'm just going to look at the bottom here. I want you to look at the bottom. We see that our reactants are NO and O3, and our products that we want to get is NO2 and O2. So how does that occur? Well, let's assume that we do have enough energy in these collisions, but now we need the proper orientation. So our blue atom is nitrogen, and our red one is oxygen. So if we see here, if the oxygen collides with an oxygen, no reaction will occur. Why? Because if we see down here, it's that nitrogen that bonds with the oxygen. And so we can't have an oxygen hitting another oxygen like we have in this first example. No reaction will occur, and our end result will be the same as what we started with. Now, what if it is the nitrogen? Well, this nitrogen is hitting this oxygen right here. However, it's hitting the middle oxygen. And if you notice down here at the bottom, this nitrogen is hitting, this oxygen is hitting one of the terminal oxygens. So it has to be one of the terminal oxygens, not the middle oxygen, because the middle oxygen would require two bonds to be broken, whereas the terminal only one. If we are assuming that double bonds are in fact just one. So in that regard, I should probably say only two bonds are being broken, not three, because with ozone, if you remember, we have, not to get super technical, but we have a single and a double, which also has a resonance structure, which from bonding you may remember that. The whole idea is that there are less bonds being broken in this example than in this example. Therefore, this middle one, no reaction. Top one, no reaction. But this bottom one right here, we do have the correct orientation. You get a reaction. You can also look at the other examples here. This one, no reaction. This one, reaction. If you want to take some time, pause the video and check those collisions out. Factors that affect the rate of reaction: physical state, temperature, concentration, and presence of a catalyst. So I want you to remember here, as we go through these four things, think about collision theory. You need enough energy, and you need the proper orientation. So if we're increasing the number of collisions somehow, then we're going to increase the reaction rate. So I'm not going to go through and read all of this, but basically physical states of the reactants is important. The smaller the particle size, the more likely collisions are to occur, because a larger surface area is exposed, which is why something in a granule or powder form even would occur much faster than if it's in a block form, like we see on the left. Temperature. Temperature is a measure of the average kinetic energy of particles in a substance. Now, kinetic energy implies that the particles are moving. This is energy from motion. So, if we increase the temperature, we are effectively increasing how fast, on average, those particles are moving, therefore increasing the likelihood that they're going to collide, and also increasing the likelihood that they're going to collide with the correct amount of energy. Concentration. So concentration increasing, we see here in these pictures that we have on the left, we have a low concentration on the left right here, and we have a higher concentration. Higher concentration means the particles are more likely to collide, and therefore a reaction is going to occur. We can see the same thing in the bottom, just with particles that are in solution, and then a block of some blue solid. Increase the concentration, and you're going to increase the likelihood that these red particles collide with blue ones, and therefore a reaction occurs. And lastly, presence of a catalyst. There are numerous different types of catalysts. I've provided a biological example here, and also one in an automobile. So catalysts, just to keep it simple, increase the rate of reaction by giving those particles an alternate pathway. And sometimes this is literally a platform for the reaction to occur on, and other times it's actually forcing those particles in the correct orientation, or guiding them, I should say, in the correct orientation to be able to collide. Either way, a catalyst is not used up in the reaction itself. So it's not part of the reaction, but it's important to speed up the reaction. And we'll talk a little bit more about catalysts when we look at potential energy diagrams. The examples I've given here, enzymes there's many different kinds of enzymes that play important biological processes. And then a catalytic converter allows literally a surface for particles to react, pulling harmful gases out of the exhaust before it expels from the car. Enzymes, most of the time, and this is what this picture down here is getting at for enzymes, it's like a lock and key mechanism. You've probably talked about this in biology. It's giving those particles the correct orientation, or guiding them to have the correct orientation in order for the reaction to occur. So let's go into potential energy diagrams. Now, if you need to take a minute to pause the video, please do. So hopefully at this point you pause the video to recap what we have gone over so far. Now we're going to jump into potential energy diagrams. So what is a potential energy diagram? Well, quite simply put, it is a diagram that shows the energy pathway of a reaction. It'll tell you the reactant and product's energy. It'll tell you the energy needed for a reaction to occur. And it will also tell you if energy is released or absorbed through the course of the reaction. Now, specifically, different pieces of a potential energy diagram. You'll get the potential energy of the reactants. You'll see the potential energy of the products. The symbol for these two things is H sub R and H sub P, respectively. You'll have the activation energy, E sub A. This is the amount of energy required to reach the transition state or the activated complex from the reactant. Now, that is a textbook definition. But as we mentioned in collision theory, that required energy for a reaction to occur, that is the activation energy. That energy needed for the reaction to begin. It'll also tell you the transition state, or T sub S. This is also called the activated complex. This is the point when the reactant particles are going to have the most energy they will have. This is the point where the bonds begin to break and new products are formed. It'll also tell you the enthalpy, or the change in enthalpy, I should say. This is the heat transfer at constant pressure. Now, don't worry about at constant pressure. This is just the definition of enthalpy. Why at constant pressure? That's a topic for an AP level course or a college level course. We're not going to get into that, but what I do want you to understand is how to find delta H. The delta H can be found from taking the energy or the enthalpy of the products and subtracting the enthalpy of the reactants. Now, you might have heard me say the words energy and enthalpy interchangeably here, and oftentimes that will be the case. Again, the difference between those two things for a higher level course, just to keep it simple, I will use energy and enthalpy interchangeably at some points in this presentation. Now, endothermic versus exothermic. Endothermic, this is heat when heat energy is absorbed by the system or goes into the system, into. Now, if a reaction is endothermic, that's going to give us a positive delta H. That means that the energy of the product was more than the energy of the reactants. We'll see that on an energy diagram and talk a little bit more about that in a little bit. Now, for exothermic, you're going to have a negative sign for delta H. This is when energy is released. This does not mean that we have less than zero energy. It simply means that energy is leaving the system. What's interesting here to note is that for endothermic processes, they're actually going to feel, pause the video and think about what they're going to feel like. You got two choices, hot or cold. Energy is going into the system. If you chose cold, you are correct. Endothermic processes are pulling heat from the surroundings. If your hand touches it, it's going to be pulling heat from your hand, and it's going to give you the sensation of something cold. That means that energy is going into the system. If something is exothermic, it's going to feel warm or even hot to the touch. Exothermic processes and endothermic processes, if extreme, can be dangerous to touch, so you should be careful in the lab. Only do so when instructed by your teacher or professor. Let's take all these concepts and look at an actual potential energy diagram. So here we have a potential energy diagram. I, in fact, did actually make this potential energy diagram. Isn't it beautiful? So let's talk about these things one at a time. So on the left right here, we have the enthalpy of the reactants. On the right, we have the enthalpy of the products. Now, if we take the enthalpy of the products and subtract the enthalpy of the reactants, which gives us delta H, are we going to have a positive or a negative sign for delta H? We are going to have a positive sign. Now, that is because the enthalpy of the products is greater than the enthalpy of the reactants. Now let's look over here at this smaller potential energy diagram just for the sake of looking at a different type of situation. Here we have the enthalpy of the products and the enthalpy of the reactants. If we take H sub P and subtract H sub R, this being H sub P, this being H sub R, is our sign for the delta H going to be negative or positive? If you said negative, you are correct. So, in the potential energy diagram we have on the left, energy is being absorbed by the system. In the potential energy diagram we have on the right, energy is being released by the system. Which one would feel hot and which one would feel cold? If you said that the one on the left will feel cold, you are correct. The one on the right will feel warm or hot. Now, what are these other things? So, I've labeled delta H right here because if you look at the difference between H of the products and H of the reactants, it's going to have this value here. Now, E sub A, this is the activation energy. This is the energy needed to get the reactants from their energy up to the point where the reaction will occur, which is at the top of the hill. Okay, so from this to here is the activation energy. That is the energy required for the reaction to begin. Now, T sub S, or the activated complex, this is the point in this reaction where the reactants are going to have the most energy they will ever have. Now, I've also labeled E sub A on here. E sub A is going to be the activation energy of the reverse reaction. So if we're going in that way, this is going to be the activation energy of the reverse reaction. Now, just because I have all of my labels in certain spots doesn't always mean that you will see those labels in those spots all the time, as we'll see on energy diagrams here in a little bit. Other energy diagrams that we're going to see here in a little bit. So catalyzed reactions. What do catalyzed reactions look like? So again, a catalyst lowers the activation energy by finding an alternate route. However, there is no change in the heat of the reactants or products or the delta H. There is, however, a change in the activated complex as well as the activation energy, because that activation energy is being lowered. Now with this blue line here, this blue line, which I'm now making red, that is without the catalyst. And then the green line is with the catalyst. So we can see that the activation energy, let's just go over here for the sake of being consistent, the activation energy for the green line, going to have that value, that's close enough green, and the activation energy for the blue/red line is going to have that value. So you can see that because the activation energy for the catalyzed reaction is lower, the catalyzed reaction will proceed faster. Now, because the activation energy decreases, that also means that the activated complex, or the transition state, will decrease. But everything else, the energy of the reactants, energy of the products, and delta H remains the same. Now let's go through an actual potential energy diagram and label all of these things that we've just been talking about conceptually onto a potential energy diagram. If you would like, you can pause the video now, copy down the potential energy diagram that I have here, and label each piece according to the definitions that we've gone over so far. Now I do want to be clear. A, B, and C are not talking about any particular values, but where something is. For example, A, that's where your reactants are. B, that's your activated complex. C, that's your products. The numbers are referring to the actual values, or I should say actual energies that those arrows represent. So if you'd like to, again, pause the video, try to do this, or you could just follow along as we go through on the video and do them. So 1, what is 1? 1 is going to be the potential energy of the reactants. 2, that's going to be our activation energy. It's the energy required to get from right here all the way up to the top of the hill. 3, this is our catalyzed reaction pathway, usually shown by a different color or a dotted line. We can see right here where it starts to break off from the original pathway. That's our catalyzed reaction pathway. 4, this is the potential energy of the activated complex. 5, this is going to be delta H, or the heat of the reaction, the change in enthalpy, or the change in energy. All of those terms could be used interchangeably, so please take note of that. Heat of reaction, delta H, change in enthalpy, change in energy. Okay, and number 6, that's going to be the reverse reaction activation energy. And number 7, that's going to be the potential energy of the products. Now, is this reaction endothermic or exothermic? It is, in fact, endothermic. So let's put some actual values to this. So we see here, and let's just assume that this is in kilojoules, because usually that's what we'd be working with. We see here we have kilojoules, and this is as time goes by, as the reaction proceeds. We can put time or reaction pathway. So use the numbers to find what is H sub R. H sub R, again, is the enthalpy of the reactants. That's going to be the value right here. So it is 150 kilojoules. What is the value for the change in enthalpy? And this sub right here, F, the subscript F, just means that I'm talking about the forward reaction. If it doesn't specifically say, always assume that it's talking about the forward reaction. If it specifically says the reverse reaction, it'll let you know. So if it doesn't say anything, just assume it's of the forward reaction. So what is delta H of the forward reaction? Again, that's going to be your difference between your products, which is right here, and your reactants, which is right about here. That value, which is about 50 kilojoules. What is E sub A, or the activation energy? Again, this is the energy needed to go from the reactants all the way up to the top of the hill. And let's say this is right between 200 and 250, so we're going to say 225. I'm estimating here. All right, and so what is the activation energy? It's going to be 225 minus 150, which is going to be 75 kilojoules. And what is the activated complex? That's from all the way down here to the highest point in the graph. That is going to be 225 kilojoules. So now let's talk about what temperature and activation energy have to do with each other and what that looks like using this graph. So on the y-axis here, we have the fraction of molecules with a given kinetic energy. On the x-axis, we have different kinetic energies, low and higher, as we proceed to the right, as you would expect. Now, right here, this is the point. I'm just going to switch colors here. That is the point where these particles have the required activation energy. Now, I want you to think about the area under either one of these curves as being equal to a particular number of particles. So, for example, for T1, we can see that right here, a much larger area exists with low kinetic energies for T1 than as does for T2. Which means that T2, on average, the particles have higher kinetic energy because the area under the curve at higher kinetic energies is larger for T2. Now, if this is the activation energy right here, the energy needed to begin the reaction, then what area under the curve is larger at or above the activation energy? Sorry, let me rephrase that question. Which curve, T1 or T2, is going to have a larger area that has the required activation energy? Now, I'm going to change my pen here to make this explanation thorough. So let's look at T1 first. T1 is going to be represented by this area right here. Those number of particles are going to have the required energy to react. Whereas with T2, it's going to be this area. Which area is larger? The area under T2 is in fact larger, which means what about the temperature T2 as compared to T1? T2 is a higher temperature than T1. This concludes the presentation on collision theory, reaction rates, and potential energy diagrams. Thank you, and have a great day.